Everyone, welcome back. So we looked at 3 different ways we can improve the coefficient performance for our refrigeration system. One is just to cool multiple things, one is to do it in a cascade style, and then the final one is to have a multi-stage compression. This just makes it so each compressor is doing less work. And so overall, compared to one compressor doing all the work, it's much more efficient. So let's figure out how to calculate this. So here we have 2 cycles, 1 and 2. The condenser is what gets rid of the heat. The evaporator is what absorbs the heat. So this is the cold side, this is the hot side, and luckily they're both orange and blue to make it easier. Now, what's this cycle doing? So let's see here. We have an adiabatic liquid vapor separation unit. Okay, nice. It's using Freon. Good to know. And the system operates the evaporator at negative 40 degrees Celsius, the condenser at 800 kilopascals, and the separator at negative 10.1 degrees Celsius. And we've got to have a 22 kilowatt cooling load. Okay, so what are we trying to find? Well, first thing is, what is our mass flow rate going through these 2 compressors? Because we have a separator right here, we can have a different mass flow rate going through each of them. Second, what's the power used by the compressors, which makes sense. And finally, the coefficient performance, because we know the power being used and how much our cooling load is, well, we can get that pretty easy. Then it says some things that I really like. One, it says that it's a saturated liquid at the inlet of each expansion valve and a saturated vapor at the inlet of each compressor. And gloriously, the compressors are completely isentropic. Are they really isentropic in real life? No, but this will give us an upper estimate rather than, a more accurate estimate. So you can't beat this for these particular settings. So let's go through it. Keeping that picture up there just going to make it a little bit easier. So first off, let's get a cycle diagram for this. So this is just a basic one I'm taking. I've got the pressures in there. I've got the temperatures. It said it was a saturated vapor at the inlet of the compressors. They're perfectly isentropic. And it said it was a saturated liquid at each expansion valve. So those points were already set for us. The basic shape you can just kind of draw. This is more than knowing what the numbers are exactly from this diagram. It's just so you know what points you're supposed to be looking at. And help you remember, like, oh yeah, that's isentropic. Oh yeah, that's an isobar. The pressure's the same between those 2 states. It helps you connect things together. So now we're going to work through slowly what it gave us. We have the temperatures. We have some, qualities. We can use that. So first off, we'll start with state 1. Why state 1? Why not? Now that's coming from the separator, and as such, it's at negative 10.1 degrees Celsius. Now it's entering the compressor, and it says it's saturated vapor. So I have a temperature, and I have a quality. And so this is really easy to find. I would just go to my tables, and I would look this up. And this would be the G properties because it's a saturated vapor. So negative 10.1 degrees Celsius for that. So I've got one enthalpy and I've got an entropy. Why did I get that entropy? Because this next process is isentropic. So I know what my entropy is at the second state, and I know what my pressure is. So I can go to my superheated tables and see that. So why don't we go ahead, we're going to jump over there so I can show you why we're going to need to interpolate and show you how we can do that. So movie magic, we'll jump over to the tables. Okay, so here we are at the appendices. We're going to go to the superheated refrigerant table right there. And this thing always jumps past it. Or did it jump to? No, it's right here. And let's see, we have a pressure of 800 kilopascals. So I'm right in this spot right here. And it said it was an entropy of about 0.92 something. So I would be right in between these first 2. And so my value is going to be somewhere in between these. So these would be the values I would be using to interpolate. This column right here is my enthalpy. If you're wondering how do I know that, you go to the top and it shows you right there. I do kind of wish that moved with you, but it doesn't. And there we are. And so my entropy is between these 2 values. And so I'm going to have to interpolate to figure out what it is. Okay, so with that, let's jump back to our problem. Okay, so we interpolated, we got an enthalpy of 273 kilojoules per kilogram. Okay, so we're doing good here. So after that condenser, we're now a saturated liquid. And so that once again gives us a quality, and also we have a pressure. So it's really easy for us to go to our saturated mixture pressure tables for Freon and to look it up. Since it's a saturated liquid, its properties are all the F properties in that table. G for gas or vapor, F for liquid. I always want to say fluid, but gases are fluids as well. Okay, now we've gone through 3 points. Let's go to the fourth. This is an easy one because throttling is isenthalpic. So our enthalpy after throttling, enthalpy before it is roughly the same. Is it actually the same? No, you do lose some heat transfer typically, but this is a magical adiabatic system. Okay, now we're going to go to point 5. We could kind of jump over to point 8 if we wanted to, but we don't quite know enough for that one yet. So we're going to go to point 5. So the separator is going to take only the liquid. So this is right here. We have gone all the way through. We entered the separator, and we were a mixture when we entered that separator. You can see that we were a mixture by looking at this point right here. And so it's taking all the liquid and sending it through this pipe. And all the vapor is being sent. Let's see here, make sure I do this right. Yes, this way. So with that, we still know the temperature, and we also know its quality, and so we're able to find from this what our enthalpy is. So since it's saturated liquid, I just find the closest temperature I can, negative 10.1 degrees Celsius, well, and I get the enthalpy of that. So I'm going to jump to the tables one more time to show you a little trick that I like to use when I'm solving problems like this. Okay, so here we are at our saturated mixture table for Freon. This is the temperature table because it gave us a temperature. Now if you look down here, what you're going to notice is that there is no negative 10.1. I've got negative 10, and so I could say, okay, well my enthalpy is going to be really close to that. If you want to be exact, that's probably not going to do it for you, and a lot of times it's not as close as that. So just because this is a textbook, typically they give you a temperature that's somewhere in the tables. It's just not in this one. So before you go interpolating, remember to check both tables, because the temperature table and the pressure table, the only difference is that you have reversed these columns. Like, there's nothing magic about this being 60 here and negative 36.95. I could have put all these values in the same table and been fine. And if you look down here, what you find is, wait a second, there's a temperature of negative 10.1. That's the saturation temperature, which I'm a saturated liquid, so that checks out. And so I can go over here and find the enthalpy for this. I get the exact value rather than having to interpolate. And so it's a lot easier on me. So this is more of a textbook thing, not like a real life thing. In real life, you're not going to have nice values like this. But hey, you're learning this, so you're probably going through a textbook. So a little trick to help you out. Okay, let's jump back to it. So separator, saturated liquid, we got that point. And now we're once again going to go through a throttling process. It's isenthalpic, so 0.6 has the same exact enthalpy. Now we're down there. We're once again a mixture, but that doesn't matter for us too much. Okay, so we've gotten 6 of the 8 points. Let's keep on going and finish those last 2. So for 0.7, it is a saturated vapor. It's a saturated vapor that's at negative 40 degrees Celsius. Negative 40, it's a nice round number, easy to find in your tables, and it's saturated vapor, so you look for all the G properties. We're going to need both the enthalpy and the entropy because that entropy is going to help us figure out 0.8, which until this point we didn't have enough information to actually solve it. So 0.8 is superheated. We aren't given a pressure for it, but luckily for us is the same pressure as 0.1 and 0.5, which we saw was 200 kilopascals, and that was from the tables. For a saturation temperature of negative 10.1, you're at 200 kilopascals. So that's another thing you can find here to make it easier on yourself. And so with that, we can then go to the superheated tables. We say, okay, my last entropy is the same as my entropy at 0.7, because my compressor right here is isentropic. I'm at a pressure of 200 kilopascals, And so from that, I can look up and find out what my enthalpy is. Yes, you're going to have to interpolate again. Is interpolation fun? No, but honestly, you can make yourself a calculator, do an Excel really, really fast. Then you can just use every single time. So do that. Make it simple on yourself. Okay, now we have all of the enthalpies, every single one, and that's enough for us to solve this problem, hopefully. So now let's figure out the mass flow rate for our evaporator. This is the easiest one because the cooling load is coming out here, and so that's going to be connected to the change in enthalpy, which we know, and our mass flow rate. So here's our cooling load, which we do know, our mass flow rate, which we don't know, and then our enthalpies, which we have just calculated. And so that difference in enthalpy, that is us absorbing heat from what we're trying to keep cold. And if we want to do it at 22 kilowatts, I think is what it said, we have to have a certain mass flow rate to match that. So we rearrange, we plug it in, and we get a mass flow rate through the evaporator of 0.1174 kilograms per second. Okay, so now let's focus on the condenser. So let's see right here, yes. So we've got 0.1 and 0.4. I've got 0.5 and 0.8. These are where the heat is being more or less exchanged. Okay, they come close to each other and then they're split off there. So the mass flow rate going through the evaporator times the change in enthalpy through the separator is going to be equal to the mass flow rate going through the condenser times the change in enthalpy going through the separator. So at this point, it acts very much like a heat exchanger, just a very fancy one. Now, I know all these values. I also know the mass flow rate going through the evaporator, and so I can go ahead and solve. As a note, if you tried to do this in the wrong order, you just wouldn't be able to solve for it, and so you'd have an equation. You've gotten here, and then you'll be able to solve it later. But use what you know. We knew something over here. That's what we started over there. Okay, so we have a mass flow rate through our condenser. So with this, we have our mass flow rates. That was our first question. Now we're going to find the total compressor work. What is that? Well, it's equal to my mass flow rate times the change in enthalpy across each compressor. Just not wanting to erase. There we go. Now it's going there. So I have 0.7 and 8 for this compressor multiplied by that mass flow rate. And then for the condenser, I have points 1 and 2 going across that compressor. So I'm saying, what's the change in enthalpy that came from my compressor multiplied by the mass flow rate? And what's the change in enthalpy times mass flow rate for my second compressor? Add them together, and I get about 8.0193 kilowatts. Okay, now let's calculate the coefficient performance, which is not that hard. We know the cooling load, which is 22 kilowatts. We know how much work it took to do that, which is 8.0193 kilowatts. And so that gives us a coefficient performance of 2.74. And so that is it for this problem. It wasn't too terrible. The interpolation for points 8 and 2 was not fun, but beyond that, it wasn't too hard. Just remember, start where you know, and then work your way slowly through it. If you find you don't know enough to go to the next step, try another point and see if you can figure out from there. Sometimes you might pick the wrong point and know enough to go part of the way but not be able to finish it. Either way, thanks for listening. I hope this helps you, and I'll see you all next time. Bye-bye.